So, okay. Yeah, Devamalya, please.
The symmetric and antisymmetric property of a tensor is a intrinsic property of a tensor. So if you find the transformations law,
Right,
the
right,
defined tensor actually, you can
right,
easily it will remain symmetric or
right,
antisymmetric.
right, right. Yeah. So, yeah, Devamalya is right. And the thing is, see, it's not just a change of basis, right? The change you are not. It is not simply a change of basis. You're taking tensors which are defined in one space and mapping them into objects which are defined in a different space. Like, I mean, so it's not simply a change of basis. But yeah, as to that question, why does that antisymmetric part not why is there that antisymmetric part? Why do we need the Gauss constraint at all? So I've put that on my list of questions. Are there any other questions? So Deva has asked me a couple of questions. One is about constraints and Lie derivatives. Another one is about this Gauss constraint and the derivation, a technical question. And then the third one she has asked is about this
Another comment I should make
symmetric property. Yeah, please.
that any second-hand tensor that is matrix valued, any second-hand tensor can be decomposed always in
Yeah.
symmetric part.
No, right. No. Yeah. That's true. So the extrinsic curvature also starts off as a covariant derivative of the normal, right? And when you decompose it, you get a trace part, which is the expansion, a symmetric part, and an antisymmetric part, which is called the twist. So when your this vector field n is hypersurface orthogonal, it doesn't have to be, right? You can take this the antisymmetric part vanishes.
Yeah, the thing is, my point is that
Yeah.
Any of the part is to be zero, then there should be a constant. Because you can always.
So Deva's question is that when we go from the metric variables to the connection variables, right? When we take KAB and contract with the triad, right, and we get KAI, the Lie algebra valued one form, extrinsic curvature one form, right? She's asking that why is this symmetricity condition not automatically satisfied? Like when I write down KAB, when I invert that equation to write KAB in terms of the extrinsic curvature one form, right? We impose this condition that the antisymmetric part of KAB is zero, right? And that becomes the Gauss constraint later. And her question is, why is that constraint? Why is that required? Like, why is that not automatically preserved? Right. So let me share my screen. I think it'll be better if I write it out. Okay. So today is lecture 9, right? Lecture 9, right? So she has asked these questions. So her question is the following: that see when we define this one form, right? What do? We contract it with the co-triad, right? And then we say that Right. So then we say that we can write KAB as, we can invert this equation to write KAB as Bj delta Ij. All right. So here we're taking this and this symmetric part, right? Okay. Now her question is that to begin with, KAB is antisymmetric, right? Sorry, KAB is symmetric. So that means the antisymmetric part is 0, right? So she is asking, then why is KAI not quote unquote symmetric? Do you see what the question is? Right. This is the extrinsic curvature, right? This is the one form. So here we are going from the one form to the extrinsic curvature, right? And so then we impose this additional condition, right? That KAB is equal to 0. And that means that EAI KBJ delta Ij is 0, right? So she is asking, why is this condition not automatically satisfied? Okay.
See, the transformation of the, may I say something?
Yeah, please.
To be wrong or kind of stupid thing. That
No, I mean,
that's mathematically, that's KB is equal to EI symmetrized with the KBJ. If there are two tetras, EIA and EJB with the construction with the KIJ, then KB would have been asymmetric tensor. Since there are only one EIA.
Right, exactly. So what you're saying is that if it was of this form, let's say Kij is equal to Kab, Eai, Ebj, right? Like this. If it was like this, then it would be symmetric. Right. But it's not of this form. So that's why symmetricity is not guaranteed. Okay. So to answer your question, Deva, it's because when we perform this contraction, it doesn't give us only the symmetric part, right? So to begin with, KB, you just think of KB as an arbitrary tensor. Okay. And so I guess your question is, why is that to begin with KB is symmetric? I understand your question. Okay. I'll need to sit down and just look at it. Right now I can't, my mind is not that.
But I'm not convinced. I mean, I have to sit and think.
No. I expect you to be convinced. Okay. I don't expect you to lower your standards. Right. Never be convinced unless you are convinced, just to make anybody feel happy. Okay. All right. So I'll make some notes about this and all these questions, this derivation that you asked. Another question she asked is, how do you derive this expression? I'll work out all these things. As I said, all these things are worked out in Theman, but I worked them out 10 years ago, and I've never felt the desire to revisit those derivations. So
in Theman, I think I looked through it.
Yeah, Theman, you have to look through Theman many times before you find what you're looking for. Theman is very, very dense.
One last comment for me.
Yeah, please.
So can you bring the previous page?
Yeah, sure.
So in the expression of KAB, where you have written a symmetric underbase symmetric, right?
Mm-hmm.
It is not the same thing I am telling in different way.
Mm-hmm.
It is not the same transformation law which we usually take in the definition of tensor.
Mm-hmm.
So that is why the intrinsic property of the tensor, whether it is symmetric or antisymmetric, is not guaranteed.
Mm-hmm. Right.
Oh, so you're saying it doesn't transform like a tensor. So the k with this a at the bottom and the I on the top is not a tensor.
So in
No,
the
no, it's not. It's a one form. It transforms as a one form, and it transforms
Okay.
as a Lie algebra element. So it transforms under local Lorentz transformations on the I index, and it transforms as uh, an ordinary tensor on the A index.
So it is a tensor. Yeah.
So anyway, look, this discussion is taking us too far. I will do my due diligence and put some detailed mathematical explanation on Zulip. And if you're not satisfied at that point, then we can continue the discussion further. Okay.
Yes, sir.
Okay. So, all right, guys. So, are there any other questions from anybody else in the audience? Okay. All right. So, let me just quickly summarize what we talked about in the last lecture, right? So, we talked about going to this. Well, we already did the triad part. Then we defined this densitized co-triad, which is actually a two-form in disguise. And then I talked about the example of Chern-Simons theory and how this functional solves the Hamiltonian constraint in the Astiker variables exactly. And then just to give you some, this provides, some inspiration for the people working on this, right? It's like the first time that you can actually solve the constraints exactly without any symmetry requirements. And then, so we start talking about the quantization procedure, right? So now, so when we quantize, generally, the normal procedure would be that you treat your fields as something that are smeared on your three-dimensional spatial slices, right? But these this connection and this co-triad, they have certain nice properties which invite us to choose a different smearing. So for instance, this is a one form, and so a one form can naturally be smeared along a one-dimensional line. And there is the natural definition of Wilson loops, which are the holonomies, right, of the connection. So it makes sense to use such holonomies as our basic variables. And this co-triad is a two form, right? It's a two form in disguise, like I said. So if you look at the definition, right, it's like you take this two copies of the triad and take the cross product, and then you are contracting with this epsilon. So if you don't contract with this epsilon, right, you can see that it's a two form. Then two forms are naturally integrated over two-dimensional surfaces, right? And so the variable to or the what should I call it, observable or function of E, which we should look to quantize, is this flux, the flux of E through any surface. Okay, and then we had a nice discussion about the effect of this E operator in the quantum theory, which I will explain in more detail today, and what happens, for instance, when a surface is intersected by a curve, and that curve happens to lie within the surface. And then Takato asked a very nice question, which was that, and then hopefully I gave a reply which was satisfactory. Okay, then I gave some other references on work that has been done to show that, well, this representation, this loop representation is equivalent. It allows us to reconstruct the usual fork representation of Maxwell theory, for example. And so today I will talk more about the quantization procedure. Okay, so let's do that. All right. So
Deepakda,
yeah.
could you please tell me again that why the holonomies are required, because I couldn't get it in the previous lecture.
So holonomies are, I mean, they're not. It's a choice, right? I mean, you don't need to necessarily do it in that way, right? You could, but because this is a one form, right? It makes sense to integrate it along a one-dimensional line. That's basically the one reason, and the other reason is the fact that such an integral in Yang-Mills theory, right, corresponds to Wilson loops, which are well-known gauge invariant observables.
Yeah, but you are assuming some non-trivial topology, right?
No, there's no assumption of topology or anything, right? I mean, it's just.
But in the but for the trivial topology, the Wilson loops should be one on a trivial, right?
No. I mean, if there is a non-zero curvature, the Wilson loops in general will not vanish, right? They measure if you have a Wilson loop, what it does, the holonomy measures the strength of the curvature through this surface, right? You can show this quite explicitly, and in fact that is the basis of this of the lattice gauge formalism, right?
But for the simple connected space, this loop always can be shrunk to point, right?
Yeah, yeah, sure, but
So the
so the if you
loop,
do shrink this loop, so you know, I mean, okay, so you can shrink it topologically. There's nothing to stop you from doing that. But as you shrink it, right, and as the amount of curvature within that loop decreases, right, you will correspondingly change the holonomy around that loop. It is like if I take a piece of wire, okay, and I have some magnetic field, right? Then I can always take this piece of wire and shrink it down. I can shrink the radius down, right? Now, but as I shrink it down, and let's say the field is time dependent, okay? So what happens is that the presence of this magnetic field, time dependent field, induces a current in the loop, okay?
Okay.
And now I can always shrink the loop down, and nothing to prevent me from doing that. As I shrink it down, it encloses less and less of the magnetic flux. So the amount of current that is generated also decreases, right? Right? And in this case, the holonomy would be a measure of the current.
Okay.
And now, don't ask me to make that analogy concrete. I mean, that would take us too far away.
Okay.
Okay. So you know, I mean, when I'm there's nothing that there's no topological obstruction in this. I mean, this is just standard gauge theory. I mean, I'm not saying anything which is you know, unconventional. Okay, so all right, so let's talk more about this quantization strategy. Okay. And there are a couple of other issues which I'm not going to address in great detail. One of the issues is regards the imagery parameter, and this imagery parameter, but you should know what this imagery parameter is, right? So now when we define this R-sticker connection, right, we define it in this way, minus IK, right? So this object is a complex connection. So what happens is that in addition to your constraints, you have to impose some reality conditions. You have to impose some reality conditions on your tetrad for co-triad, right? Because your co-triad also becomes complex. Okay. So if you want to get the real valued Einstein equations, you have to impose reality conditions. And there are all sorts of technical issues with imposing these reality conditions to be able to get the quantum theory. At least there were initially in the mid 90s when this issue was noticed. And so somebody, I think Barbero, right, came up with the idea that he showed that you can take this parameter gamma to be any real or complex valued parameter, and you can still for this value, for any value of gamma, you will get a set of constraints which remain equivalent to Einstein's equation. So for instance, the Hamiltonian constraint takes this form, epsilon jk EAI EBJ FKAB, right? So this is the one that we have seen before. This is the one we'll call it H0. And we get another contribution which corresponds to this gamma term, and it involves some co-triad and some extrinsic curvature terms like this. So now when gamma is equal to I, plus or minus I, right, what happens? The 1 plus gamma square vanishes, right? And we get back our normal R-sticker constraint. So, so the question is that what is this gamma doing, right? What is the source of this ambiguity? So now the thing is that you have this action, if you remember the Palatini action. So we obtain I think there is that E term here. We obtain we start from this, right? This is a starting point. We do the decomposition using this action. So it turns out that we can add a certain term to this Palatini action, which looks like as follows. So let me, it will be SP plus epsilon mu nu alpha beta E mu I in J F mu I J. So what this term is called the Hol's term after the author who first suggested it. Yeah, Devamalya will talk about these punctures and all. Okay. So one can start with this whole term along with the Palatini action and perform the 3+1 splitting, and you will get this modified Hamiltonian constraint. And the thing is that the reason this term does not affect the dynamics is because it is identically zero. It vanishes on shell. Okay, and this is because of the Bianchi identity. So if you do the variation of this with respect to the tetrad, you will get the equation of motion will look like this: epsilon mu nu alpha beta e nu j f. So yeah, 1 second, I made a mistake in my indices. It should be alpha beta e alpha I, let's say f mu nu I j, let e, right? And there is something I'm missing here. I forget what it is, but yeah, this will give you zero. I think because of the second Bianchi identity. Okay. Now, right. So this and gamma is a coefficient here. What is the Holst term? Let me. I think the Holst the gamma comes here as a coefficient. I think it looks something like this: gamma times gamma squared plus 1. I believe that's or I don't know, maybe something like gamma squared plus 1. So again, it vanishes when gamma is equal to the complex imaginary. Okay. So there is a lot of debate about whether this gamma is a physical parameter, whether it affects physical observables, but you know, again, we will not venture into all of those. It will take us too far afield. Okay. So now let us come to the discussion of the quantization procedure proper. All right. So we have decided to work with these flux holonomy variables. All right. And now the question is, how should we, what form should this, should our states take? Okay. So we have decided, right, that one of our variables is the holonomy along any line segment. Right. So if I have A, B, I associate the holonomy along this line segment as G of gamma as the path ordered exponential of integral of this AI, the connection, along the path, right? So these are my basic variables, right? So how do I define an arbitrary state? So actually there is a whole this thing technical aspect related to the definition of generalized connections, again, which will end up not making a difference for us. Okay, so generalized connections are what you have is that, so you have the space of connections and you have the set of gauge transformations. Let's say G, right? And then you would identify your physical connections as the quotient of the with respect to your gauge transformations, right? So these would be your physical connections, right? Because will include its elements will cannot be related to each other by Gauge transformations, right? That's the definition of the quotient. So what happens is that if you want to work with these one-dimensional variables, these holonomies, you have to define something called generalized connections. And generalized connections are basically functions which can be arbitrarily discontinuous. So for instance, one can have a connection which is defined only along a loop, but away from that loop, right, it might be zero. So there can be like the loop is there is a discontinuity where this loop is, right? You can think of it as a Dirac string or something like that. So you get these this state or space of generalized connections, and then you also get a certain space of generalized Gauge transformations. You take the quotient, and that gives you the physical set of connections on which you finally construct your states by taking functionals which are defined on elements of this set. Okay. So I am not going to go into great detail about that. Well, so first, before doing all of that, first let us ask what is the space of Gauge variant connections. So we want to have states which are functions of holonomies. Okay. Now, what does that mean? That means you have some connection of one-dimensional lines. They could be intersecting, they could not be intersecting, right? And with this set, okay, let's call this set of lines. It could be loops. There could be intersections. There can be loops. There can be all kinds of structure. Let us say associate with this set the state which is a functional of the holonomy along each loop. Okay. Right now, we are not familiar with such kind of state, right? Because we normally think of functions which are defined as, let's say, functions of some spatial coordinate, right? Or some momentum coordinate, right? But here, what we are saying is that what these lines are doing is that they are probes, right? So you have some geometry, and you want to probe that geometry. So what you do is you sprinkle these lines everywhere, and when you do that, right, there will be a certain holonomy along each line. So that becomes your quote-unquote coordinate. So you choose that holonomy as your so you choose your states to be functions of these of the holonomy along each loop. Okay, and in general, this gamma is some graph, right? So it can have disconnected components or connected components. It doesn't matter, right? It can be a bunch of completely disconnected lines. It can be a bunch of loops. In general, it's a graph, right? And so these, just one second, I'm getting a call. I'll just Okay, I'm back. Sorry for that. So, okay, so we have some functional of these holonomies, and we will. So the one reason why we are taking these holonomies, right, is because we want to construct states which will be invariant under gauge transformation, right? And how should you do that? Well, you should work with something which has that invariance property, right? So holonomies, these group elements, right? They transform under the effect of gauge transformations, right? But if you take the trace of the holonomy, that remains invariant. So to construct the states, the first step is to take functions of this kind, right? All right. Now, okay. So the picture that one can think about is like you have some graph, and along the edges of that graph, you have these group elements are assigned to each edge, and the state, the function is some function of these group elements. Okay. Okay. So now let's see. All right. Now we want to, but this is not. These functions are not very convenient to deal with. All right, because for one thing, you can see that how you can have literally an infinite number of such graphs, right? So and so the question is, which graph should you use? And if you do take some preferred set of graphs, working directly with these holonomies is again not very convenient. So what is done is there is something called the Peter-Weil theorem, and this plays a very critical role in ordinary quantity. Our state, and we write it as the sum of some set of modes, right? E to the I px minus omega t a dagger, something like this, I px plus omega t a, right? This is how we write our field. So what we would like to do, and the Peter-Weil theorem allows us to do, is to take these functions of these holonomies and write them in terms of spin variables. Okay. So how do we do that? So let me tell you what the Peter-Weil theorem says. So the Peter-Weil theorem is the statement of Fourier transforms for functions which are defined on groups. Okay. So here's the statement, first of all, that if you have a function that is defined on a group, and a holonomy is a function, is a group element, right? And these are functions. So this is a function on n copies of the group, right? Psi is a function on n copies of the group. So if you take a function on any compact group, right, and the compactness condition I believe is important, right? So for any compact group, you have some representation, right? Where this is the group representation matrix, right? G is the element of the group. J is the it labels the representation, right? So for example, if you are working with SU2, then this J, right, takes values which are half integer, right? Half, 1, 3 halves, 2, and so on. And so in this expression, these functions play the role of our plane waves, right? So in order to be able to do a Fourier transformation, the Fourier transformation rests on an ordinary momentum space. It rests on the following fact, right? That if I take something like this, x times p minus p prime, this gives me the Dirac delta function, right? This is what the Fourier transformation rests on, which is another way to write it is that if I take this, it is right that there is a certain set of orthogonal states which happen to be represented by plane waves. So if you don't have this orthogonality condition, right, you couldn't do Fourier analysis. So group representation matrices satisfy a similar orthogonality condition. Okay, and this can be written in the following way. I will explain what these various terms mean. Okay, so this is called the great orthonormality theorem. Right? There are two such theorems for groups. This is one of them. So what this says is that if you take any two representations, so J and J prime are different representations, and you take M and N prime and N prime, right? These are not the same, right? So you take any element of the group representation matrix and any element of another group of the same group element, but in an arbitrary representation, and you integrate over the group manifold using the Haar measure. Over the manifold, which is the group manifold, which satisfies the requirement that it is invariant under translations along the manifold, right? Generated by where H is some element of the group, right? So it is left invariant and right invariant under translations generated by group multiplication. So the existence of this theorem allows us to write down any function on a group in this way. Okay, so let's see. I can write down any function in this way. So I have a sum over all of the representations, right? So what is this doing? This is like a dipole expansion of a function, basically, right? Where when you write down, for instance, some function in spherical harmonics, you sum over all the L values, right? This is similar to that. And what are your orthogonal components? The orthogonal components are these elements of the group representation matrices. And now we can use this theorem, right? So we can take our F and we can integrate it with something like this: m prime n prime f of g. Okay, so this is just like in Fourier analysis, right? You write down f of x is equal to some f of p e to the I p dot x and sum over p, right? And so that's what we are doing here. So, and now we can insert this. If we insert this expansion in here, what will we get? We'll get du mu g, this g m prime n prime. F of g can be written as fj mn times dg mn, and there's a sum over j mn, right? And now these coefficients f, they don't depend on the group element, right? Just like these coefficients don't depend on the position, right? And now we can use this orthonormality theorem to integrate this product of these representation matrices. And so what it is, we will get this with these delta functions. So we'll get something like j prime j, delta m prime m, delta n prime n, fj mn. And when we sum over j mn, what will we get? We'll get fj prime m prime n prime. Okay, so we can obtain these coefficients by using this group orthonormality theorem. So this fact is known as the Peter-Weyl theorem, which says that for any square integrable function, on a compact group manifold, you can write the you can expand a function in this way, right? And what is this expansion? This expansion is just you're writing out a sum in terms of this is like a Fock space, right? So where you are associating a Hilbert space with each spin, with each representation. So there's a Hilbert space associated with spin half, spin 1, spin 3 halves, and then your Hilbert space for a single group element, right, or for a single copy of the group would be a tensor product of all the possible representations. So let me, go back and show you how that works out. So if we write down the Hilbert space associated with a single holonomy, the Hilbert space associated with a single holonomy or single edge, E is the edge, is the group, is a set of square integrable functions with respect to the hard measure on the group, right? So this is the Hilbert space for a single edge or a single line, right? Which is the simplest graph. And then using the Peter-Weyl theorem, and then the Hilbert space for the whole graph can be written as a tensor all of where this E belongs to gamma. right? So you take all the edges in your graph. You take all the edges. For each edge, you have some Hilbert space, and then your total Hilbert space is this tensor product, right? So this is just a many-body state space. Okay, but the more important thing is that the Hilbert space for each edge can be further decomposed, and let me. I'll share this with you guys. I've written up a recent for a paper which is a work in progress. I've written down this procedure in fairly sufficient detail. Okay. So why is this possible? So how do we deconstruct the Hilbert space of this? Okay. Now the thing is that we can view each such matrix as a map from the Hilbert space of the jth representation to itself, right? I mean, that's what group represent. That is what group this thing. That's what these representation matrices do, right? This matrix. It acts on a vector space. Which vector space is that? That vector space is the 2j plus 1 dimensional vector space, right? So if j is 1/2, your vector space is 2-dimensional, right? It's a space of spinors. If j is equal to 1, your vector space is a state of, your vectors, just 3-dimensional vectors. And then what does the group element do? It takes one vector and converts it into another vector, right? So if you have some vector v, which belongs to your Hilbert space, your vector space h of j, and then I will write v as using this index notation. Okay, let's say like this, where this is some basis of h of j. Then what does the group? What is the action of this matrix? It gives you another vector whose components are related to the old ones by this multiplication. Okay, that's it. I mean, there's nothing mysterious about this, right? So for let's say G is equal to SO3, and these vectors V living in R3, right? What is this matrix for some element, right? It's a 3x3 rotation matrix basically, right? And when I take this rotation matrix and I act on any vector, I get another vector. No big deal, right? So what is this? This is the rotation matrix associated with with G, and this J is equal to 1. So R of G acts on any vector to give me another vector, right? So R of G is a map from R3 to R3. Okay, I hope this point is clear. Like, there is nothing mysterious about it, so it should be clear. If it's not clear, please tell me. So Deva, Rizwan, Deva Malya, yeah, anybody, please.
Oh, I have a question.
Yes, Takata, yes.
So how do you define the dimension of vector? In case of SO3, it is somehow, well, trivial, but so so where the dimensional vector given by the dimensional gauge group?
So whenever you have, I mean, the dimension is just, if you are working with the jth representation, right?
Yep.
So J is the spin, right? So spin half, spin one, so on. Then the dimension of your vector space is 2J plus 1. Right? So for J, what is your associated dimension? 1/2, you get 2. For 1, you get 3. For 3 halves, you get 4, and so on. Right? So if you just look at the SU2 angular momentum algebra, what are these? These are the allowed eigenvalues of the angular momentum operator. Right? If you just start out with your usual angular momentum algebra.
Yeah, I understand this point, but
Okay.
The function fg is given by a linear combination of some various representations, right? So
that's right.
what is the state? Right. It is a linear combination of different vectors belonging to different dimensions.
Exactly. Exactly. That is true. So it contains components corresponding to all the possible spins.
I see.
Right. Yeah. So very often what we do is we end up working with, we that J is equal to 1/2, and in very many cases that restriction is justified. But yeah, in general, arbitrary spins contribute to a general state. Okay. So
So truncating higher spin contributions give approximation to the Hilbert space.
Yeah.
I see.
So yeah. Wanted to.
Okay, I got it. Thank you.
Okay, all right. I mean, this is just like what do you call it? You have some function, let's say r theta phi, right? And or f l l m theta phi, right? So here, all of the L values and the M values, they contribute to this function, right? The same thing. Okay. All right. Okay. So now, because we can view these group elements as maps from the vector space to itself, right? So therefore, if you look at a function on the group, right? So this function is an element of L square G. So now f of G belongs to L square G, right? And f of G can be written as, again, at the sake of being too overly repetitive, it can be written in this way, right? So this can be viewed, so it can be written as a direct sum of maps what you can view this function, right, as a map from this tensor product to the complex numbers. And because you're summing over all the j's, you get this direct sum over here. Is this okay? All right. So now, if I look at the Hilbert space of the whole graph, the Hilbert space of the whole graph corresponds to the set of square integrable functions defined on n copies of the gauge group, where n is the number of edges. Right. So in the case that we are interested in, it becomes n copies of SUN. Okay. So this is the decomposition for a single edge. So if you want to write down the decomposition for the whole graph, what these? So this is for a single edge. Okay. So we will write it like this: J of E, right? This term, Hj of E, tensor product Hj of E. So this is the Hilbert space of a single edge. And if I take the tensor product over all the edges, I get the Hilbert space for the whole graph. All right. Now, I mean, maybe like some of you might not be, it might not be clear why I can think of these functions as maps from two copies of the Hilbert space. So I mean, I hope that if you think about it, it will be clear. Okay. So one very simple way to see that is that, right, this acts, if you look at the rotation matrix, for example, a rotation matrix, if it acts on one vector, it gives you another vector, right? But I can also take a rotation matrix and contract it with two vectors, right? In that case, what does it become? It becomes a map from V cross V to R, right? So I can write this rotation matrix as a map from V cross V to R. That's it. That's all we are saying here, is that this matrix can be thought of as such a map. Is it? I hope it's the explanation is a little bit clearer now. Deva, Rizwan, any questions? Deep Malya, Pritam, Haridhar sir, please. You are there in the audience. Please correct me. I mean, if I'm saying something incorrect. Okay.
Can I ask you a question?
Yes.
Well, I'm not sure the number of edges you wrote n here. Is this well defined? Because a product of two group elements given another group element, and I'm not sure how the number of edges are defined.
So the number of edges just depends on right. I mean, like I said, the number of edges is arbitrary. It depends on the graph. Your graph is a probe, which is probing the geometry of your space-time. And right, and so you can have your graph. It can be as complicated as you want it to be. It can just be a single loop or a single open edge. It doesn't matter. Or it can be, it can form some sort of lattice. It can be an irregular graph, doesn't matter. It's some graph.
Oh, well, my question is, for example, let us denote a group element which takes A to B as a G1 and B to C as G2. And
when you say A to B and B to C, you mean certain points, right? So A to B and B to C. So let me just draw that. Okay, you have some points A to B, and then you have another edge connecting B to C. Okay. Then you have some group element here and some group element here, right?
Yeah.
And so and so you can write G1, G2, and that's what you're saying, or G2, G1, I guess, is the one that takes you from A to C, right?
Yeah.
Along the union of this path, right? G2, G1.
Yeah.
Okay, and then.
And so the number of edges of the above graph is 2, and the graph below is 1.
I see what you're talking about. So this becomes this structure. If you look at it in such cases, okay, this structure will always reduce down to, it will become just the Hilbert space for a single edge. Okay, I mean you could take this path and subdivide it.
Yeah.
But because there is this requirement which is precisely this requirement, that if I take a path and I start with a path with some G, then I choose to divide this path to pieces, okay? Such that this is G1 and this is G2. Then I have the requirement that the original group element G is equal to G2, G1, right? This is a constraint, right? I mean, which has to be satisfied. So if you impose this condition on whatever functions that you define of G1 and G2, all of your Hilbert spaces, right? They will all collapse, and you will end up with just one Hilbert space. And this will become more clear when I talk about intertwiners in just a little bit. And intertwiners
to define the number of edges, you need to first consider constraint and apply.
Right. So how do you define the number of edges? The number of edges becomes defined when you look at the graph. An edge is defined as a path which connects two vertices. Okay, so these are vertices, right? And each vertex has some valence. So for instance, this vertex is 3 valent, this vertex is 3 valent, this vertex is 4 valent. All right. So you define an edge as a path which connects two vertices which have valence greater than 2. Okay. Or alternatively, you say that an edge that you don't consider such pieces. You don't consider breaking up such pieces, because if you do break up such pieces, it doesn't matter. It reduces all to one Hilbert space at the end.
Yeah, now it's all clear. Thank you.
And also you will have edges which are associated with loops, for example. So one has to, can't just, one has to be a little bit more careful. But again, with a loop, right? So here you have edges, which this is sort of a degenerating example. Another example is you could have a loop like this. But again, this is a path connecting one trivalent node to the same trivalent node, right? Right? And closed loops, they will not, they will contribute to your state space by some phase factor, right? So that those will just be your vacuum bubbles. And when you look at physical expectation values, these things will just divide out, the same way as they do in the usual Feynman diagrams.
Yeah.
Let me insert a few more pages. Okay, this is a point that you have raised, and it's very important to clarify.
Okay, thank you.
Okay. Now, once we have, so now we have this Hilbert space of a graph. Okay, and let me write it down again. It's L square SU2n, tensor product over all the edges, direct product over all representations living on an edge, and then tensor product of the two copies of the Hilbert space. All right. Now, let us think of this edge as connecting two vertices in the graph. You have two vertices, V and V prime. Okay. And again, this is a non-degenerate edge in the sense that we have just discussed. Let's call this edge EVV prime. Okay. And this is a directed edge connecting these two paths. Right. Now we can associate. So you have two different Hilbert spaces right here. You can associate one Hilbert space with each end of the edge, right? And that is also true, right? Because on the edge you have a holonomy. The vectors living in this space. Right? So we can write down this edge Hilbert space, right? This thing. We can write it in the following way. Same thing, direct sum over all the representations. But now I will label these two Hilbert spaces with a label which tells me which edge, which vertex that Hilbert space corresponds to. So I can just use one label. I don't need two labels here. I can just write V and V prime. So this tells me that this Hilbert space is associated with the source vertex. So this is called the source vertex, and this is called the target. Okay. All right. Now, alternatively, it helps to use a slightly different notation, where V, the source vertex, V, I will write that as in this way, VE plus, and the target vertex, V prime, as VE minus. So this would just be V again. So then I will write this Hilbert space of a single edge as JE, and then here I would write VE plus I don't know if this actually simplifies the notation. Each edge. Now let us look at the this full state space one more time. It's the tensor product over all edges, sum over all representations of this VE plus JE tensor V minus JE. Okay. Now you can see in this decomposition, we can do a little bit of rearranging. Okay. So I'll bring the direct sum out, this tensor product. And I will write the remaining terms in the following way. Tensor product over E plus goes to this E plus V, and I'll just explain what these terms mean respectively. VE plus, and then tensor E minus EV minus SJE VE minus. Okay, so this space vertex. What do these various terms mean? So I have a vertex, okay, and let's say that there are some edges that are coming into the vertex and some edges that are going out of the vertex. All right, and so we will refer to all the outgoing edges as a set of all the outgoing edges as EV plus, and the set of all incoming edges we can write as EV minus. Okay, and I think that also justifies why I am referring to the source vertex as EV plus and the target vertex as EV minus. Right, so because the incoming edges, the target vertex of these incoming edges is V, and for the outgoing edges, V is the source vertex. So
Deepak,
yeah,
I thought that the plus and minuses were used to refer to vertices, not edges. I'm slightly confused now. Why we are referring to pluses and minuses and referring to edges when we do it.
right. So that, okay. So first, I said that you have an edge, a directed edge, right? And I referred to, so this is the source, this is the target, and I called the target as V E minus. Okay, so what this means is this is the vertex which is the target vertex of the edge E. And VE plus means it is the vertex which is the source vertex of edge E. And the reason we want to do this, we want to decouple, right? We want to be able to write down the decomposition of the Hilbert space as a tensor product over vertices rather than over edges. And so if you look at this, let me draw it in a little bit more detail. This is a vertex. These are the incoming edges. So associated with the incoming edges, right? I have the Hilbert space, and so this is, let's say, E1, this is E2, this is E3, E4, right? Then I have a Hilbert space associated with this end of E1, and this Hilbert space, I put a minus, right? And a minus, and there's a plus and a plus. Okay. So I don't know if I mean, so let me just complete this, and then we'll look at it again. So now the point is that the Hilbert space for the whole graph can be written as a sum of the Hilbert spaces for, and right, and the tensor product of all of these Hilbert spaces is the Hilbert space associated with the vertex. So in this case, for instance, this would be this H1, H2, H3, H4, H1 tensor H2 minus tensor H3 plus tensor H4 plus. Okay, and of course there's a J label also. I've not included that, but if you include the J labels, then it would become like J1, J2, J3 plus J4 plus, like this. This would be your Hilbert space associated with this vertex. It's the tensor product of the Hilbert space associated with all the target vertices and the Hilbert space associated with all the source vertices. Does this make any better sense? I don't know.
Yes, it does.
And then now we can write down finally the state space of a full graph is simply the tensor product of all of these Hilbert spaces, right? So what did we have initially? What we had initially was that our Hilbert space for each edge. So this is the edge. I can write this as H minus E, and this as H plus E, right? And again, I mean, I should include the J labels, because the J is a parameter, right? And then let's say I have another edge over here. So this is, let's say, E prime, okay? And this is going into the vertex, and I would write this as, so I think my notation was this, that's minus. So I would write this as minus, and then this would be JE prime, right? And this is some other vertex, and this Hilbert space is H plus JE prime. And this JE prime is the same over here. And for this graph, or this segment of the graph, this is the tensor all the edges. So in this case, there are two edges, E and E prime, and then a direct sum over all the representations associated with each edge, and then a tensor product. Thank you, sir. Thank you so much for sticking around. I realize that this is running rather long, so thank you for coming here. Haridas sir has to go. Haridas sir has actually done some really nice work. If you guys refer to his papers, you will see that. Okay. I think Tebo Malya also maybe has left. maybe I didn't answer his question satisfactorily. I don't know. So this will be tensor product over JE, right? And then we are wise position. So this will be JE plus tensor JE minus, right? Plus JE minus, and then this whole thing tensor the sum of all right, guys, can you hear me? I got disconnected. Okay, and so alternatively, this thing can be written as so JE minus and JE prime minus. I can take those separately. JE minus tensor H JE prime minus. These are the Hilbert spaces. This one, I'll put it in a different color. Let's say orange and orange. And so this is orange. And then these two Hilbert spaces, let's say red, 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 red. These correspond to the other two vertices, right? So I can now do this vertex-wise decomposition rather than an edge-wise decomposition, right? And then there's, of course, a direct sum over JE and JE prime, all the possible JE. So what does this achieve? This achieves a change from the edge-based variables to vertex-based Hilbert space, right? So earlier what I had was my Hilbert space was a tensor product over all the edges, and I have shown that it can be written equally well as a tensor product of Hilbert spaces associated with all the vertices individually. So once again, each edge has two Hilbert spaces. I can associate those two Hilbert spaces with the two ends of the edge. So I can, and the tensor product, the Hilbert space for the whole graph is the tensor product of all of these spaces and then summed over all the representations. But equally well, I can look at all the edges which come into a single vertex, collect all the Hilbert spaces around that vertex, right? And then take the tensor product and the direct sum after doing that. Right, so this allows me to define the Hilbert space associated with a single vertex. So let me do that first. So the Hilbert space associated with a single vertex can be written in this way. Tensor product, all the incoming vertices okay, and all the outgoing vertices. That's basically what it means. Right, and so these J's are not necessarily the same. Okay, so that's why here I should put a curly braces to indicate that this is the set of all J labels associated with the incident edges. Okay, so another way, so these are some edges. Now I say that this edge is in J1 representation, J2 representation, J3 representation, and J4 representation, right? And the Hilbert space of this vertex is what? It's just edge J1, tensor edge J2, tensor edge J3, tensor edge J4. Okay, that's it. And the Hilbert space for the full vertex would be, I mean, without reference to any, would be the direct sum over all possible J labels, right? So you can have different J labels, you can have arbitrary J labels, but later on what happens is that what we find is that there is something called a closure constraint, which puts restrictions, which is basically the Gauss constraint, and that is another way to say that angular momentum is conserved, and that restricts, that puts a constraint on which possible combinations of the J values are allowed. Basically, the J values have to satisfy that sum of the total angular momentum coming in and going out of the vertex is 0. So I'll leave it here for today. I think this is more than enough. I don't know why Devamalya left. I hope it's not because he was unhappy with my answers. I mean, I understand that at some point, you know, skepticism might start seeping into the minds of the viewers. Maybe that skepticism is a function of my of deficiencies in my presentation, or maybe that skepticism is just due to the fact that this is new. This way of thinking about states and Hilbert spaces is simply not what people are used to. So, but let's say that for the sake of speculation, that you wanted to write down you wanted to define quantum states of graphs, okay? Just for the heck of it. I mean, graphs are nice things, networks are nice things. They are in use all over the place. So why not think of the quantum state of a graph, right? So how? Well, if you go through the steps, what you would end up with is the same thing. And then one more important point to note is that the reason there are two Hilbert spaces associated with a single edge, right, is because I mean, these edges are labeled by holonomies. Holonomy is a map from one Hilbert space to another Hilbert space. But another way to think of it is that if you have a gauge transformation that acts on your manifold, then the way the gauge transformation affects the holonomy of a single edge is as follows. That if you have a gauge transformation from your manifold to, you know, which is some function from your manifold to the group, how does this act on a single edge? Well, the holonomy associated with a single edge transforms as the gauge transformation acting on the source times the UE times the inverse of this gauge transformation acting on the target of the edge. So you have an edge. There's an associated holonomy U of E associated with this edge, which is some SU2. And then how should this holonomy transform under this gauge transformation? Well, you can show from the definition of the holonomy as the path ordered integral, as the path ordered exponential, that so there is this gauge transformation at the source vertex, and there's an element gauge transformation at the target vertex. So how does it transform? It transforms in this way. The proof I will you can, well, I'll point you to references where the proof is given. Okay. So this gives us a geometric picture. This gives us a picture of quantum geometry. These edges, they carry quanta of area, and vertices carry quanta of volume. And you know, it's not just something that is an analogy. You show it explicitly by writing down what the area operator is in these variables and what the volume operator is in these variables. Okay. So that will be the topic of the next session, and hopefully you all will stick around for that session. So, Takato, questions? I really like the things that you ask. So
Yeah.
So question.
Oh, well, did you answer my question on the left? You will answer later.
Which question? Right. So do you want me to talk about that now?
Oh, well, either is okay, but as time is running out,
because
so maybe.
No, so your question was that, first of all, are spin network states variational states?
Yeah,
right?
yeah.
And now,
right.
so the thing is that well, I mean, any quantum state is a variational state, right? I mean, as long as it depends on some parameters, and those parameters can be variable. So, but more, I think the better question is that can you relate these spin network states to matrix product states, or to the tensor, or to the state defined on a tensor network in general?
Right.
Right. And I have shown that you can, that they are in fact identical. Okay. Because what happens is that when you look at the Hilbert space associated with this vertex, you end up associating something called an intertwiner, which is an invariant tensor. And it is an invariant tensor which lives in this Hilbert space. And the invariance property is a consequence of the requirement of gauge invariance. So you have a tensor which lives on the vertices, and you have states which are living on the edges, right? And how do you evaluate the full wave function? You just contract. You contract the tensor at each vertex with the state that is connected to that vertex, right? And you do that for the whole graph. Now the difference is that in this picture, in addition to these vertices and edges, you also have this decomposition in terms of representation. This is the element that is not normally present in the tensor network picture. Right? In the tensor network picture, you work with like lowest spin generally, like you just work with spin 1/2 states.
Right.
So if you restrict yourself to just spin 1/2 on each edge, or given spin, whatever it is, given j, then you get a tensor network. And that's the straightforward definition. And one can show it quite explicitly. As I was saying, that there is this paper which is a work in progress. So let me. So yeah, I'll share this. I was writing a paper on the relationship of some SPT phases, which are symmetry projected topological phases, to look quantum gravity. And because it's a paper that involves condensed matter and LQG, I've included a very comprehensive appendix which describes all of these constructions.
Mm-hmm.
Because for a condensed matter theorist to read this, and well, you know, there should be enough material for them to be convinced that you can indeed write a spin network wave function as a tensor product, as a tensor network state. So this is the final expression that I obtain for a spin network wave function. All right. So these I's are the vertex intertwiners. These J's are the edge labels. These D's are the are matrices associated with the edge degrees of freedom, and these A's are basically so this D tells you what is the weight for each edge, and A tells you what is the weight for each vertex, and you sum over all the vertices and edges, and then you sum over all the possible states. And
well, the graphical picture is quite different from tensor network, right? Because tensor network, the boundary free legs carries the Hilbert space state.
Right. So in this also the boundary legs carry the Hilbert space, right? Because each edge has two Hilbert spaces associated with both the ends of the edges.
Mm-hmm.
So if there is an edge which is not connected to any vertex,
I see.
that edge will still carry that Hilbert space, right?
Mm-hmm. Right.
And so it actually has the interpretation of corresponding to a fermion.
Mm-hmm.
And I mean, or a boson. It just depends on which J representation you use, right? But it has this thing. So yeah, I mean, it's the same thing. This is what I mean. This is why I think, you know, that I feel very happy.
Yeah, it's quite surprising and really fascinating.
And the thing is that people are just not familiar with this spin network picture, right? So they don't understand like many of these little things. And so, you know, in the minds of many people there is enough room for confusion, because they look at the two and they're like, they sort of look similar, but you know, there's this issue and there's this issue and there's this issue, and nobody has like actually sat down and addressed all of those issues. So if you write down the state for a tensor network, right? So I have in this table here, what is the state of a tensor network? It is given by a site Hilbert space, some bond dimension, vertex tensors associated with each vertex, where you have this IV, which is the physical index associated with, you know, whatever physical degree of freedom is living on the vertex, and you have some internal indices, bond indices. Then you have some edge tensors, where again you have some edge labels, and then you can have possible physical indices living on the edges. So how do you write down this the state, this tensor network state for an arbitrary graph? You sum over all the vertex tensors and all the edge tensors, and yeah, and this is exactly the same as the representation that you get when you look at the spin network wave function. So again, I mean, I might have made a mistake in there somewhere, but you know, barring any obvious mistakes, I think this is correct.
Yeah, that's really fantastic.
So I mean, since you're familiar with both languages, maybe you can have a look at this and tell me if I'm saying something which is correct or something which is just incredibly wrong. Right. Okay, so I'll stop here. I think we've had enough of a long session today. Stop the recording and